So this conical frustum thing here, I have taken the approach that felt like the most obvious to me, given that I have a computer in front of me to handle the heavy lifting of the integration. So I've just done an integral of the surface area from 0 to h to get the volume of the liquid. Remember that there were kind of 3 different approaches. You could use any of them. You could also just use the formula that is linked in like the Wolfram alpha formula and use that as well. I went ahead and actually derived it. So we know what the volume is going to be. Just a little bit of a tip here. I know that most of you quite like to use, well, everybody likes seeing the formulas more nicely typeset like this. But if you're hoping to use this formula in a Python program somewhere, it is quite useful to have it in this linear form that you can just copy and paste into a program. Unlike this, you can't easily do that, but this you can. So if you just print that, you don't have to switch back and forth between the notebook modes. Like if you print this, the thing, it'll kind of print in a copy-pastable format. So you'll see it uses nice proper Python notation, for instance, for the powers. So I have produced this Python file over here, and that is the deep magic that I've used to get that formula from SymPy into this function, right? I have copied on the one side and pasted on the other side. And I just want to show you in terms of modeling where we are with our, we've mentioned before that there's this idea that on the one hand we have these purely theoretical models, F equals ma, dv dt equals in minus out, right? And then there are these empirical relationships. And I've tried a little bit to kind of say, well, you know, when you zoom out far enough, there's no difference between empirical and theoretical models. They're all based on fitting data anyway. So we're going to fit some data now. So we're going to use this file that I've produced here. So here's for that particular experiment what this relationship looks like. So this is the level that this person has measured as it changes over time, like the obvious way to model this problem. And remember that I told you to write down 3 different equations, right? So we've got a relationship which is effectively the mass balance simplified down with the constant density assumption, dv dt equals minus f out. We've got a geometry thing that we've just spoken about, which is just how the cup geometry relates the volume to the height. And we have the hydraulic relationship, which is something about how the level relates to how quickly stuff flows out. And we've got an impression, at least some strong idea, that you know, a cup that is full drains faster than a cup that is empty. And so we're going to kind of try and see what that relation looks like. So the thing that I thought of, this is relatively smooth, so I just fit a polynomial onto that. So I fit a polynomial onto this mostly because I am trying to calculate derivatives. And it's very easy to calculate the derivatives of polynomials, right? And why am I trying to calculate derivatives? Because I want to investigate, I have these hypotheses that dv dt is equal to some function of the height. And I want to see what does that function look like. So I'm going to be plotting lots of different derivatives of things as a function of height. Now, kind of the obvious version of this problem, if we had been really good at math, we could theoretically reduce those 3 equations down to 1 equation, which is dh dt is equal to some function of h. We'll look at that as well, and we'll see in this case, my sense is that it's not going to be great. So I'm going to fit this polynomial onto that. Most of you, hopefully by now, know that if you start with something like numpy dot, and you start writing stuff and you press tab, you'll get this nice expanded version of all the things that start with poly. All of these things are things that you can do with polynomials, right? So you can add them together, you can take derivatives, you can divide them, you can fit them, you can integrate them, you can multiply them together. The way that NumPy stores these polynomials is as arrays that contain the coefficients in descending orders of the polynomial. So if it's ax squared plus bx plus c, you'd have a, b, c as the array that maps to that. So I do hfit. I'm going to fit a 4th order polynomial, polyfit. I'm going to evaluate that 4th order polynomial using a finer mesh so that I get a nice smooth curve instead of just straight lines connecting the dots. And when I plot that, I get this beautiful fit. Look at that. That's really nice. Now, please note that this beautiful fit is not physically meaningful. It doesn't really relate to any model that you could say, oh yes, well, this is the well-known Sandrock model of height. It's just a fourth order polynomial. I'm just fitting a smooth line. I'm doing that because I would like to calculate the derivative of that. Now, I'm also doing this for the cup volume. So that's what the height looks like over time. This is what the volume looks like over time, taking into account the geometry that we've taken. So let's see if we have a chance of modeling this system as dh dt is equal to some function of h. So what I've done here is I've calculated the derivative of the height by just using the polynomial derivative functions, and I'm going to be plotting that derivative as a function of height. So this is the derivative of the height, this is the height itself. And as we can see, this is not the most intuitive version of this. I would expect, for instance, for the derivative to be large when the height is high, and for the derivative to get progressively smaller. So I'm at least expecting some kind of a monotonic function to kind of match my intuition of how things are going to happen. It turns out that when we do this for volume, that looks a lot more like what we expect, right? So now I'm saying this is dv dt as a function of, or minus dv dt, call that f out, right, as a function of h. Now that looks like something we can work with. That looks exactly like I said, large f out at the beginning and getting smaller and smaller as the height goes down, right? So I've also not been very prissy about the units. I've just used millimeters, so all of these are weird, right? So like the height unit is millimeters and the flow unit is millimeters cubed. So be it. It's nicer than working with SI units in this particular case. And then lastly, I'm just going to do take a constant, which is kind of the mean ratio between the rate at which the thing is changing. And that's kind of our initial stab at a model that relates. So this is assuming that there's just a constant, that the rate at which stuff goes out is just proportional to the height. As you can see, that's not awesome. But the other model in 2.4, the square root model, doesn't work that much better. Now, a little bit of what we're going to be learning in this whole situation is a solid piece of skepticism about how well the equations that are in the book describe the real world. I'm hoping that after doing this, you ask yourself, so how close are those equations that I learned in COP and that I'm going to be learning in CIO to real equations or true equations with a capital T? Given that we are really struggling to write down a model of a little plastic cup with a hole at the bottom.